Welcome back to another episode of Data Dive, where we explore the intricate world of databases and the technology that drives them. Today, we're diving into a topic that's fundamental yet often misunderstood: transactions. We'll unpack what transactions are, why they matter, and how they can be both a blessing and a curse in database management. So, grab your headphones and let's get started. To kick things off, let's clarify what we mean by transactions. At its core, a transaction is a sequence of operations performed as a single logical unit of work. You can think of it as a way to ensure that a series of changes to a database either all happen or none happen at all. This is crucial for maintaining data integrity, especially when multiple users are accessing the database simultaneously. Now, you might be wondering why we need transactions in the first place. They provide several safety guarantees, often summarized by the acronym ACID, which stands for Atomicity, Consistency, Isolation, and Durability. Each of these properties plays a vital role in ensuring that our data remains accurate and reliable. Let's break it down. Atomicity means that a transaction is an all-or-nothing proposition. If any part of the transaction fails, the entire transaction fails, leaving the database state unchanged. This prevents partial updates that could lead to inconsistencies. Then there's consistency, which ensures that a transaction takes the database from one valid state to another, adhering to all predefined rules and constraints. It's important to note that consistency is somewhat application-specific. While the database can enforce certain rules, it's up to the application to ensure that the data being entered is valid. Next, we have isolation, which is about managing concurrent transactions. When multiple transactions are happening at the same time, isolation ensures they don't interfere with each other. This is often formalized through the concept of serializability, which guarantees that transactions appear to run in a sequential order, even if they're executed concurrently. Finally, durability guarantees that once a transaction has been committed, it will remain so, even in the event of a system failure. This typically involves writing data to non-volatile storage, like a hard drive or SSD, and may also include replication across multiple nodes to ensure data safety. But here's where it gets a bit tricky. While these properties sound straightforward, the implementation can vary significantly between different database systems. What one database considers ACID compliant might not hold true for another. This ambiguity can lead to confusion and misinterpretation, especially when vendors use the term ACID more as a marketing tool than a strict guideline. As we've seen, the rise of NoSQL databases in the late 2000s introduced a new paradigm. Many of these databases opted to abandon traditional transactions altogether or redefine them to offer weaker guarantees. This shift was often justified by the need for scalability and performance in distributed systems. Some argued that transactions were the enemy of scalability, while others maintained that they were essential for managing valuable data. So, how do we navigate this landscape? Understanding the trade-offs is key. While abandoning transactions can lead to improved performance and availability, it can also result in data inconsistencies and integrity issues. This is where the concept of BASE comes into play, which stands for Basically Available, Soft State, and Eventual Consistency. BASE systems offer a more flexible approach, but come with their own set of challenges. Let's take a closer look at the ACID properties. Atomicity ensures that a transaction is treated as a single unit. If a transaction is interrupted, say due to a crash or a network failure, all changes made during that transaction are rolled back, preventing scenarios where some changes are saved while others are not. Consistency, in the context of ACID, is not about the database being free of errors, but rather about it being in a valid state according to defined rules. For example, in a banking application, the total amount of money across all accounts must always balance. If a transaction violates this rule, it's up to the application to correct it. Isolation is critical in multi-user environments. Without proper isolation, you could encounter race conditions where two transactions try to modify the same data simultaneously. For example, if two clients increment a counter at the same time, without isolation, you might end up with an incorrect final value. Isolation levels like snapshot isolation and serializability help prevent these issues, but they can come with performance costs. Lastly, durability means that once a transaction is committed, it should survive any subsequent failures. This means that the data must be written to a reliable storage medium, often involving mechanisms like write-ahead logs to recover from crashes. However, achieving perfect durability is a challenge. If all copies of the data are lost simultaneously, there's not much that can be done. Now let's talk about the practical implications of these concepts. In real-world applications, knowing when to use transactions is crucial. Not every operation requires the full suite of ACID guarantees. In some scenarios, you might prioritize performance over strict consistency. This is where the decision-making process comes into play, assessing the needs of your application and the potential trade-offs involved. As we move forward, it's essential to recognize that the landscape of database technology is constantly evolving. With the rise of distributed systems and cloud-based solutions, the challenges surrounding transactions are becoming more complex. In our next episode, we'll delve deeper into the specific challenges that arise in distributed databases, exploring how different systems handle transactions and what that means for developers and businesses alike. In summary, transactions are a foundational concept in database management, offering essential guarantees that help maintain data integrity and reliability. While the traditional ACID model provides a robust framework, the rise of NoSQL and distributed systems has introduced new paradigms that challenge our understanding of transactions. As we navigate this evolving landscape, it's crucial to weigh the trade-offs and make informed decisions based on the specific needs of our applications. Thanks for tuning in to this episode of Data Dive. We hope you found this discussion enlightening and that it helps you better understand the complexities of transactions in databases. Don't forget to subscribe for more insights into the world of data, and we'll see you next time.